can start now.
So, okay, welcome to this live session on Engineering Mathematics 2. So, I do not see many queries so far. I also have interacted with my TAs and they are every week, whatever queries you have, they are clarifying. So, there was one query which I can find. So, let me just clarify that first and then maybe I can brief you some important topics. So there was one query that FZ has it's a defined pole at infinity. So probably it was not mentioned in the lecture. So it is that defined pole at infinity. So it is same as basically. Let me just say here that if FZ has a pole of order m at z equal to infinity, it means that f1 over z. So instead of z, you take f as a function of 1 over z. And then so here, let me just write down. So if fz has a pole of order m greater than equal to 0, so some order at z equal to infinity, if what you will look for, you look for f1 over z. So if this f1 over z has a pole of order again m greater than 1 at z equal to 0. So instead of looking at infinity, you look for this new function which is just you can obtain by replacing this z by 1 over z. And if this function has a pole of order m at z equal to 0, which we have already discussed that what is a pole of order m at z equal to 0. So then there were several ways to test this, to check this. And then we can say that this fz has a pole of order m at infinity. So that was the query which I can see in this spreadsheet so far. And there are no other queries. So I will wait for your queries on this YouTube live. Meanwhile, why I thought that I will just brief you once again a very important topic which was taught in this module on numerical analysis, that is the iterative method for solving system of linear equations. So this is indeed a very, very important topic because whatever or most of the real life problems when we solve using PDEs or ODEs, we end up with a large system of equations which we need to solve numerically. So here we will brief some basic methods which can be used for solving such underlying system of linear equations. So there are basically the two methods, the very fundamental, very basic methods, Jacobi and the Gauss-Seidel method. So, but main point which is discussed in this lecture is the convergence, which is very important. And I do see one more question there. It was about the convergence of a sequence. So that will be also partially covered now in this portion itself. So before we start, we have to just look at some aspect of the linear system. So a linear system appears in this form AX and is equal to B. Here the matrix A can have this M cross N dimension, that means M rows and N columns. This is a column vector, so N cross 1, and then the right hand side is M cross 1. So this is a very general AX is equal to B, a system of linear equations we can have. And this system is called balance system, which we will actually look for now for solving using iterative techniques. And it is called overdetermined when we have more equations than unknowns in the system. And this is called underdetermined system if the number of equations are less than the number of unknowns. So these are the three scenarios. Very often you will see this when you have the square matrix. And indeed, in this lecture, we will not talk about the overdetermined and underdetermined system. So we will be sticking to this balanced system. So again, for the balanced system, we have the possibility of unique solution, and this is already covered in engineering mathematics 1, that when the rank of the matrix A and the rank of the matrix, augmented matrix, so when you augment this B there with A, so if the two ranks are equal to the number of variables there, then we say the system has a unique solution. And when the two ranks are not equal, then we will say the system has no solution. And of course, when the two are equal, but it is not equal to n, it's less than n, then we call the system has infinitely many solutions. So these are the few situations where we have unique solution, we have no solution, or we have infinitely many solution. The overdetermined system, so we have the unique solution. Again, when the three ranks, these two ranks are equal to n, so the same situation. And the no solution when the two ranks are not equal. So the two ranks are equal, then actually we have consistency and there are possibilities of having unique solution or infinitely many solutions. But if these two ranks are not equal, then simply we don't have a solution in either case. And again, the same situation, if the two ranks are equal and less than n, then we have infinitely many solutions in this case also. And for underdetermined system, we don't have a situation of unique solution. So we have these two scenario. One is when the rank is not equal, so the no solution. And when the rank is equal, then you have infinitely many solutions. So there is no situation that you can have a unique solution in this case. So this was just an overview of system of linear equations, and we will be talking about when m is equal to n, and indeed when the unique solution exists. We'll be talking about now how to solve using iterative methods. So what are these iterative methods, and why do we use iterative methods? What are other techniques? So I will brief you first. So if we talk about the solution methods, there are basically two distinct approaches. One is the so-called the direct method, the other one what we call the iterative methods. So what are these direct methods? Let me just name a few and then you will get the idea, and what are its merit and properties we will also talk about in brief. So we have the Cramer's rules, which you already know. We have the Gauss elimination. We have covered in engineering mathematics 1. We have Gauss-Jordan. We have decomposition methods. So there are many more methods which comes under this category of direct methods. And the iterative methods, so we have Jacobi, Gauss-Seidel, and then CG method, and then again the conjugate residual methods, and so on. So there are many methods in this category too. So what are the basic differences between the two kind of approaches we have? So the deliver exact solution. So this category here of the methods which we are naming as direct methods, they deliver exact solutions. So here, if you leave the rounding of errors, then we have actually the exact solution of the problem. This is what we have in the direct methods. Whereas in the iterative methods, as the name suggests, that we are going to have some iterations and then we will get some approximate solution. So these iterative methods, they deliver only approximate solutions. So that is somehow the drawback here, but there is advantage, and because of that we use iterative methods, and that is actually when we talk about large system, so we cannot use any these direct methods. It's going to be very expensive, and we cannot solve those large systems. and then these less expensive methods, which are direct methods, comes into the picture. Okay, so as I said, my focus would be more on the convergence part, because this is very, very important while discussing these methods. Otherwise, we can tell the method and then you can easily solve the problems. That is fine, but we have to discuss about the convergence. So the convergence means that because we are talking about those iterative methods, so you have a series, you have sequence of approximate solutions. You start with some initial guess, and with this initial guess you continue updating this, so you get a better solution and hope for the better one, and so on. But this sequence, we have to analyze whether we are going to get to the limit, which is actual solution of the problem. So that is a limiting situation. We probably will end before that limit achieves, because that is going to be like n approaches to kind of infinity situation. Then only we can get that exact solution. So in all iterative methods, we have to have some stopping criteria, and before that, depending on our demand of accuracy, we will stop that iteration. But our method should be a convergent method. Then only we can use that method. Otherwise, if it is not a convergent method, you will get some results which have nothing to do with your system. So very, very bad, or it may diverge. In fact, you can get something like very, very large values and so on, and that is not exactly the solution of the given system. Well, so matrix. So this is one where we start with, because this is one condition which is very, very easy to check, and then we can actually tell whether the given method is going to converge or not. So this is the first one where we check the diagonally dominant by rows. So a matrix A is called diagonally dominant by rows if diagonally dominant by rows. So we are here summing up all the rows except the diagonal entry. So if the absolute value of the diagonal entry is bigger than the sum of the rest values, when you have sum with the absolute value, in that case we call that it is diagonally dominant by rows. So, and then you have to check for each row. So in each row, this should happen that the diagonal entry in absolute value is larger than sum of all other values in that row. So it is called diagonally dominant by columns. If it is other way around, when you talk about the sum in this direction, the other direction, in the column direction. And the above inequality holds in a strict sense, so we call it strictly diagonally dominant by rows or by column respectively. Yeah. Okay. So and so this is one point which we need here to discuss the convergence of these methods, and a number associated with the matrix that is often required in analysis, that is the matrix based algorithm. So we have to define these matrix norms. So what are these matrix norms? They give you some notion of the size or the distance between the two matrices. So it is not very easy, because you don't have just two real number and subtracting or by the number itself you have the notion that it is a large number or it is a small number. When you have the matrix, you have several entries in the matrix, and we need some kind of notion which one number can tell you some information about its size, about the difference between the two matrices, and so on. So we define some norms. So without going much into the detail, because we will be just covering the portion which is actually fulfill our need here for discussing the convergence. So one is the so-called the Frobenius norm. So here the Frobenius norm. How to get the Frobenius norm? You just square each entry and sum all the entries, nothing else. You square each entry of the matrix and then square it and get the square root done there. It is called the square norm. So given a matrix, you can easily find out the square norms. There are many norms, so we are discussing just few very simple one which we can test on our given system there. So this was for the matrix here. I just also stated that when we x is a vector, this norm corresponding or the similar norm we have in the vector also, where you square each entry of the vector, each component of the vector, and then take the square root. So then there is a so-called row sum norm, as the name suggests, that you sum the rows, and then out of these sums you find the maximum one in each row, and that is what we call A infinity. And in vector setting also we have the infinity norm. Similarly, the column sum norm, where you sum the columns and then find the maximum one among all these sums of each column, and we have the so-called column sum norm. Or here also in case of the vector, we have also one norm which is defined in this. So the point is here that these are some, as I said, these norms will give you some notion of the size, and very important applications. Here itself, we will see that based on these norms, we can really predict the behavior of the numerical method. One very important relation we have to use it in some of the portion while discussing these convergence part, that is the compatibility of norm and the vector and matrix norm which we have seen. So they follow actually these relations. All the matrix and the vector norms I have stated here, they fulfill these inequality. So the left hand side, if you take a closed, this is also a vector norm here. So with this vector norm of Ax is less than or equal to the matrix norm, the corresponding, if you are talking about 1 or infinity or Frobenius, whatever. So here the Frobenius is compatible with this 2 norm. So you can take this if from any norm of this matrix and then the corresponding vector norm, here also the same vector norm, and this inequality will hold that Ax, the norm, is less than equal to A and X. Yeah, norm A and norm X. Well, so the iterative method, a method for solving the linear system Ax is equal to B is called iterative. If it is a numerical method computing a sequence of approximate solution xk. As I said before, what is iterative methods? We start with some initial values of the, so that is the initial guess for the solution itself, but that can be very rough guess. Sometimes we start with 0 0 0 or 1 1 1 something. You have to start with something, and then you supply to the formula, the iterative formula, and you will get a better and the better values. Better in the sense that they will, after few iterations, these values will be approximating the solution of the given system. This is what the iterative methods does. So what is the basic idea of these iterative methods? You consider a system of linear equations, Ax is equal to B. So this is a very general idea I'm just explaining to you. The idea of iterative scheme is based on splitting. So this is based on splitting of A. So for instance, so this different splitting will give you a different iterative method. So for instance, this is a very general setting. Let's A is split into P and N, like P minus N. So there, as we will see in few examples itself, we will be deriving two iterative methods, the Gauss-Seidel and Jacobi. You have a particular type of splitting of this A. So once you split, but this splitting will be is common in all these iterative methods. So, and where this P, so the one matrix there, you will always see it's a non-singular, otherwise you cannot make that iterative method. So then Ax is equal to B, you have here this splitting here, P minus N or P plus N, whatever way is, a sign does not matter. It's just for the simplicity of writing a formula there. and then this non-singular part you keep with the x, and the rest you bring to the right hand side. This is the idea here. So the px is equal to nx plus b you have, and indeed now we are almost done here with this, because the idea, or to set up this iterative method, would be that the left hand side you take x. So p is a singular non-singular matrix, we can take inverse there. So you have p inverse and nx plus this p inverse b. So this is the in all the iterative methods, when we set up, we have this kind of splitting, that left hand side you take x, and the right hand side again you take something of x. So this is what we have here, and then you can set up. So once you have the initial guess, you can put it there, the right hand side, and the left hand side x will give you the new value. This is what the idea is. So this p has been taken care now to the right hand side. So this is our iterative method. So if you supply here, let's say k is equal to 0, so the initial value, then you will get x1. So g times this initial guess plus h times b, you will get a new vector here, and this is what we are calling the values after one iteration. And then you will get, so you will get a sequence here, you will get x1, you will get x2, you will get x3, you will get x4, and so on. You will get several, the sequence, and what we are looking for, that this sequence, whether we are getting to something x exact. And this is what the important point of analysis here would be. This matrix is very, very important, which comes with this, which sits with this x there. In all the techniques or the two we'll discuss, you will see there. This is called the iteration matrix, because the property of this iteration matrix will decide whether the sequence will converge to this exact solution, or it will not converge to the exact solution. So the convergence, which I have already told you, what do we mean by convergence. For that, we also need sometimes this error, because as I said, you are always going to be, stop at some point, and that time you need error. So I'll get you to your questions. There are coming some questions. So here we are covering up to, in this live session, let's say, up to the 6 weeks, that is going to be this numerical analysis part and the first vector part. So, and then in the next live sessions, we will take about the Laplace Fourier and so on, because there's some question on Laplace transform, but we can take up to the next lecture, or we'll see if time permits, we will do here itself. Okay, well, so let me just finish at least this portion which I have started with this, the idea of the error. So the error is, there are two ways to define the error. Naturally, that the first is this one, which is the actual error. So you have the iterative solution xk, and then x here is the exact solution. So the difference between the two, you get, of course, a vector here, but that vector ek, we can take again some norm of this vector, and this will be actually the error vector. But there is another possibility of taking error, because here we need this exact solution. And in many cases, of course, in all cases where we are solving numerically, we don't know the exact solution. So here, therefore, theoretically, it makes sense. But when it comes to practice, this is not going to help you much. But there is another approximation which can be used to stop those iterations, or to say that our methods is producing a good enough approximations. This residual is very useful, because the b is known, the a is known to you. So our system, remember, is ax is equal to b. So we are looking for x. So this multiplication ax must be very close to b, and this is what exactly we are looking here, that we are making this error vector or residual vector saying b minus axk. So this will give you a good idea if it is very close to 0, all the components as close to 0, or we can take some norm, then you will get one value if that norm is very small. we say that yes, this vector is very small in length, in magnitude. Otherwise, so based on this, we can stop those iterations. So this is very, very useful. Okay, so this is already covered, and let me just go through quickly because you have already the lecture, you must have seen, observed before. So this is the splitting we are talking about. So for instance, we have this system, the A is split into the L, D, and U. So the lower triangular matrix, the diagonal only, and the upper uh, triangular matrix. So here the given A, you take this portion U, and then the rest you put 0. So this is going to be your U. You take this lower portion as L, and the rest everything you put to 0. That is going to be L. And then you take these diagonal entries and the rest everything 0. That will give you this D. So you have the lower triangular, the diagonal one, and the upper one. Well, and having this now, Ax is equal to B will be written as L plus G plus U is equal to B. And then this dx, so this is the portion which I want to keep it here. If none of the, I mean, these diagonal entries are 0, then we can easily invert this one, this d here. So assuming that none of the diagonal entries is 0, and then the d inverse will exist definitely in that case, and we take the d inverse to the right hand side, and we are actually done with setting up the solution. And this is precisely the Jacobi method we were talking about. And here this minus d inverse L plus U, this is going to be the iteration matrix for the Jacobi method. And so now we can introduce these iterations. Just left hand side you put k plus 1, the right hand side k, this x you put k at iteration, and then k goes from 0 and then 1, 2, and so on. So this xi k plus 1 is 1 over aii bi minus this one. Here this is just written in the component form. So if you write these d's and L plus U and this d inverse, and then here you have the vector which you are getting, after this multiplication, the new vector. But here we have just written that in component form. So this is also very easy to see, and we'll check in one of the examples that how to get it simply from the given differential equation. Well, so this was the Jacobi method. Either it's written in this vector matrix form or it's a component form. So let me just go through this component form. What it says that you have 1 over aia, so you are dividing with that diagonal entry. You have the right hand side bi for the ith component, and then the minus this, so aij, xj, and j is varying from 1 to n, except this j is equal to I. We can split this into two portions. The one, the summation is when j is less than I, and the summation where j is bigger than I. So this is still the Jacobi method. The difference comes in the Gauss-Seidel method. The only difference is that here we are using xk, so the kth iteration values to get the k plus 1th iteration values. While the Gauss-Seidel method, the idea of the Gauss-Seidel method is to use the latest values, That means if you are talking about the ith, for the ith component, the k plus 1th iteration, then all the values before this I, that means j less than I, because you have already evaluated those. So let's use those values itself. So this k plus 1th iteration, so the present iteration which is going on is still here. Everything was from the previous iteration. Here we have exactly from the new iteration. And if you put in the matrix form, then again here, because of this k plus 1th, with the L you will have k plus 1, and then once you write in this x is equal to gx form, so you will get this matrix vector form, and here this g is going to be the iteration matrix. So for each iterative method, the two we have seen, and there are many more, we have iteration matrix, which is actually very, very useful, or it's a very crucial parameter of any iterative method, because that will decide whether this method will converge or not. So a quick example, and then we will just talk about exactly the conditions of the convergence, and then we can discuss some of your queries there. So consider the following system of equations, and as we have discussed, so it's very simple once you have, so for example, the Jacobi method you want to use here, even you don't remember this formula, it's a simple one. So you have 13, so the x you take from here, the left hand side x, you have 13 minus this y minus this 2z and 1/5, and put this one iteration there, and the right hand side the 0th iterations. So if you go with the initial guess 111, you can compute this x1 itself, and that is done here as 2. Then the y from this equation and z from this equation we will set up. So y from here again 12 minus x minus z, 12 minus x minus z, and then we have kept these iterations there. And again, if you put this value at 10 by 3, similarly from the last equation, you will get 7 by 4. So the system of linear equations, we have this, and if you want to use the Gauss-Seidel method, the only difference when you are computing this x from the first equation, there will be no difference. You have the initial values, you have to use the initial values, the value will be 2. That was also the case of a Gauss-Jacobi method. But when you use the second one, for instance, in the Gauss-Jacobi method, this was used as the 0th time. But now we have this x1 available, so why don't we use this x1 here? This is the idea of the Gauss-Seidel method, and then we get a new value. Similarly, in Z, this x is already there, y is already available, so we will use those values, and we will get the new value. So similarly, the same example you can also do using exactly preparing your matrix, setting up your G matrix, and then by this matrix vector product, you can get all these values. So for instance, this was for Jacobi method. You put all these D, L, and U in the Jacobi method, you will get this iteration matrix for the Jacobi method. Once you have iteration matrix, you have this iterative scheme. Put the initial value there, and just solve these matrix equations, and you will get directly in one go all the entries of your next variables, your next iteration. Similarly, in the Gauss-Seidel, again, you have to set up this here, put it there, and then you will get this iterative method here, which again, after simplification, you will get this one. And then you need to simply put this x0, or then once you get x1, you put x1 there, you get x2, and so on. So after putting this, you will get these new values after one iteration. Again, this new value, you put it here, you will get the next iteration, and so on. You can keep on moving this. Iterative method. So yeah, this is important here for the convergence, the necessary and the sufficient conditions. So here there are few sufficient conditions which you can test and guarantee that the iteration will converge, and there is a one necessary and sufficient condition. So this is actually more important because it tells you everything, whether it will converge or it will not converge. So the result says that the iterative method converge for any initial guess if and only if all the eigenvalues, so here the application of the eigenvalues coming into the picture, eigenvalues of not A, of G, the iteration matrix, has absolute value less than 1. So this is the most important result of this topic, that if all the eigenvalues of G are less than 1 in modulus, in that case, we say that this method will converge. If it is greater than 1, then the method will not converge. So this is also called the spectral radius. This largest eigenvalue, the largest absolute eigenvalue, is called the spectral radius. So sometimes we call that if spectral radius is less than 1, the method converge. Otherwise, it will not converge. So A is a square. This is the background of this result actually. So one can show that if the spectral radius is less than 1, then the power a power m of a matrix, any matrix, when m goes to infinity, this is 0. So one can show this. You can go through these results again. And the main proof where it comes from the error. So if you form the error equation, actually it comes in terms of this g, in terms of this g as g power k e naught. So the error equation for these iterative methods takes the following form, that the error here at kth iteration is equal to g x power k and e naught, the beginning, the error at the very beginning stage. So if this g x k, when k goes to infinity, so infinity means you are talking about really large iterations, so this g k will go to actually the 0 matrix, and then if you multiply, you will get, your error will go to 0. So this is the background of that result, that the spectral radius is less than 1, then this error will go to 0. And another result which comes into the form of these norms here, because there is some relation. So the sufficient conditions, so these are the sufficient conditions. See, finding out this eigenvalues could be tedious in many cases. So otherwise that result is beautiful. It is absolutely complete, that you have the idea of the convergence and the non-convergence. When we are talking about the sufficient conditions, you can only guarantee the convergence. You cannot tell anything about the non-convergence there. So here about the convergence, we have the sufficient conditions. So if any norm is less than 1, if any norm, you can take Frobenius norm, you can take row sum norm, you can column sum norm, any other norm. If it is less than 1, the method converges for any initial guess. Because finding out this norm is much easier. Finding out these norms much easier than, for instance, getting those eigenvalues. So A is strictly diagonal by rows, and then the Jacobi and the Gauss-Seidel method converge for an initial guess. This is the second sufficient condition, which is actually very easy. So this is the first condition. Usually we check that if A, because here you are talking about directly at A, which is a given quantity in your system of equation. So if A is strictly diagonally dominant by rows or by column, then this Jacobi and as the Gauss-Seidel method, they converge for an initial guess. The only problem in the sufficient condition is that if you don't have this strictly diagonally dominant matrix, then you cannot say anything. You cannot say that it will not converge. Or the norm is greater than 1, then you cannot say it will not converge, because then we don't have any result. We cannot conclude anything. Then probably you have to go the necessary and sufficient condition, meaning that you have to find the eigenvalue. That is the last one. So here also, this, because finding matrix norm is much easier than finding those eigenvalues. Therefore, this is the idea. So here's the proof that why this matrix norm works, because any matrix norm is bigger than this spectral radius. And if you are talking about that the matrix norm is less than 1, so definitely the spectral radius will be less than 1, and we have the convergence is guaranteed. And the strictly diagonally dominant also, we have given you the some idea that how it is working. And then there were several examples you can find in these online lectures, which says that how this norm works. For example, this was the Gauss-Seidel method iterative matrix. We have computed the one norm which was greater than 1, so we cannot conclude anything. We cannot tell it will converge or it will diverge. Then you have infinity norm, and then also end up with 1, so it's not less than 1. Again, we cannot conclude anything. But then if we found this Frobenius norm and we observe that, okay, this is less than 1, so that's all. So here the less than 1 implies that this method will converge. Gauss-Seidel method will converge. So this is one way. The first, you have to look for whether the matrix A is in the form of this diagonal dominant form. If not, can you make it a diagonal dominant and then apply the method? If you cannot do anything from there, you cannot conclude anything from there, then you can conclude from this construction of the iterative matrix, and then you can claim. So here, then some comparative studies was done that which actually confirms that in advance you cannot say anything that the Gauss Seidel is better or the Jacobi's method. There were several examples where one performs better than the other one, and it depends exactly on this spectral radius. So here, for example, the Gauss Seidel spectral radius is 0.16 and Jacobi is 0.40. So the smaller the spectral radius is, the better convergence you will realize, which you can see here also. So the Gauss Seidel converges much faster than here. After 15th iteration, you got these values, and after 6th iteration, you got these values, which are very close to the actual value, if you just see, because these are also truncated up to 4 decimal. But the other example, if you look at the Gauss Seidel is 0.16. No, this is already discussed. There is another example where the spectral radius of Gauss Seidel is more than the spectral radius of Jacobi method, and this is greater than, in fact, 1. So we know that the divergence, and this is exactly the divergence. You started with some initial guess, and then these values you are getting, which even clearly you can see from the values that it's really going to other direction. They are not converging. So without any analyzing the matrix, iteration matrix, it is very difficult to tell that which method will converge faster, whether Jacobi or the Gauss Seidel. For instance, for this matrix A, if you just look at the spectral radius, which I have computed, it is like 0.4. Here it's 1.3. So this says that the Gauss Seidel will converge, whereas Jacobi will not converge. It will diverge. It will fail. Here, the Gauss Seidel will not converge, and then the Jacobi will converge. So it could be other way around also. And in the third example, we have seen here that because this Gauss Seidel, the spectral radius is less, so the Gauss Seidel will converge faster and Jacobi will converge slowly. But on the other hand, in this example, you can see the other results, that the Jacobi will be faster than the Gauss Seidel. So there's all these possibilities can happen, which we have demonstrated here in this in various examples. These are the three most important results. In fact, the first one is the most important, which tells necessary and sufficient condition. So once you have the idea of the spectral radius, if it is less than 1, then it will converge. If it is greater than 1, it will not converge. So you are concluding everything here. But in sufficient conditions, but of course, here the spectral radius, finding spectral radius is difficult. Therefore, we have these sufficient conditions also make sense. These also make sense. And we have this, just wait. So the last slide, and then we are almost done here. So here we are talking about this, that if any norm is less than 1, then the iterative method will converge for any initial guess. That is also easy to check, and the most easy one is the strictly diagonally dominant. If you can check this, you can find out this. So definitely the method will converge. But from the first one, even you get the idea how good convergence is, because if the spectral radius is small, it will have the faster convergence. So your error will go to 0 faster for smaller spectral radius. So this was all, and I think we have some queries here. Let me just see what are those queries. Okay, so it's something on Laplace, so I think we will discuss in the next live session. So t power n integration of gamma n plus 1, this, so the proof. Okay, so I think we have done in the lecture already this proof of like Laplace of t square and so on, and then you can generalize for any n. So this was already done in the lecture, so you can just go through that lecture. Otherwise we will I will prove again later on. Okay, so introduction to coding. So this course is not for coding actually. So this is, to provide the basic of mathematics, so which covers several topics. As we have seen, this numerical analysis is there, vector analysis, and then we have the Laplace transforms, the Fourier series, Fourier transform. So this is on that. So the coding portion is not done here. Okay, this course will help in gate preparation. Yes, definitely it will help in gate preparation, because you can see that numerical analysis portion must be there in gate, and this is very, very useful once you clear this, and also some vector portion and so on, this Fourier series and so on. So everything, it's because we are going quite in depth, so it's not just introducing the methods. For instance, here we could have just introduced to you how to work with Jacobi method, how to work with Gauss-Seidel method, but it was done little more than that, and all these details like the convergence and everything is discussed. Well, so what is one more question is there? How to check for a removable singularity in a complex integration? So we don't usually check the removable singularity there in integration. So singularity was discussed separately as a one section there. So go through that singularity portion first, and the complex integration we have done before. So why to check this removal singularity in complex integration? So I didn't get this question. And okay, so Sagar is asking for provide problem solving videos. Okay, so if you are we are providing enough problems in this tutorials, and if finding it difficult to solve it, you please comment, you write to us, and then we can provide more details, or we can explain some of those problems. This is what I understood, and there are many problems which we have also included in the lectures. So if you, I'm sure that you can go through the lectures, all the problems, and do those problems which you are providing in the problem set, and that should really help you. So if you have any further queries on like problem sets, if you're not able to solve some of the problems, you please get back to us. We will provide the solution. Yeah. And what I always request, that whatever queries you have, you please give me well in advance. So we are circulating you this spreadsheet. You mention your queries, because once I have your query, I can prepare those in a slightly different way than it was introduced to you in the lecture, and that will definitely help you here. So any query you have, just post it before live session, and then we can interact here. So I will present that, I will explain to you, and then during this interaction you can again pose your queries for those a particular problem. So you feel free to from now onward you can post your queries, and then in the next live session I will clarify those. Depending on your queries, we can have more live sessions, definitely. But just if you ask something now itself, then we have to prepare it, we have to see which lecture it was done and so on. So it will unnecessarily take much time of yours and mine. So you provide your queries well in advance. So I think there are no further queries. So I must thank you for your attention, being with us here, and see you again sometime later. Yeah. So thank you very much.